I just realized my microphone was muted. All right, guys, welcome back. This is another lecture here. I'm going to do something a little bit more different today. I'm going to record, I'm going to cover two topics at once. We're going to do section 4.8 and 4.9 here. The reason is section 4.8 covers row spaces and column spaces, and section 4.9 covers null spaces. But when you're finding these things, it's somewhat easier just to do them all at once, right? So I'm going to cover them at the same time because they're done similarly. Prerequisites, pretty easy. Row echelon form, and spanning set terminology. We need to know spanning sets and the concept of being able to write an infinitely sized set as a span of a bunch of vectors, because that's what we're going to be finding. Okay, so what are we talking about when we're talking about row spaces, column spaces? Let me get a matrix up here. So I've got 1, 2, 3. I'm going to use our standard lazy matrix here because by happenstance it happens to be pretty interesting. Now I can view this matrix as in several different ways. On the one hand, I can view this as a 3 by 3 array of numbers, right? I've got 9 entries in here. But alternately, I could view this as a collection of row vectors, right? I could view this as row vectors, which would be, well, the first vector would be 1, 2, 3. Second one would be 4, 5, 6. And the last one would be 7, 8, 9. Okay. I could view it as a collection of column vectors. Okay. At which point in time the first vector would be 1, 4, 7. The second one would be 2, 5, 8. And the last one would be 3, 6, 9. And you see these collections are different, right? Yeah. Just as this is also this is also different from, let's say I'm viewing it as, again, an array of 9 different entries, right? So 1, 2, 3, etc. So in the case where I'm looking at the rows and the columns, well, it's somewhat natural to ask ourselves, okay, so I've got all of these different, I'm just going to use the rows as an example, but this applies to columns too. So I've got all these rows. Well, let's say I want to use those rows to span something, right? Because again, that's something we tend to do with our matrices a lot. We tend to apply elementary row operations, which are just linear combinations of these vectors. And if I apply linear combinations of these, that eventually will give me the entire span if you take all possible linear combinations. And so, of course, again, it's natural to think, well, what's the stuff I can span from the row vectors? Okay? What's the stuff I can span from the column vectors? And these things are called the row space and the column space. Okay? So the row space of some matrix A is the span of the row vectors of A. And similarly defined for the column space, which we typically write as col space, just because column is a bit long. Okay? But again, that's just the span of the column vectors of A. Now, that's nice. If I wanted it, couldn't I just put span in front of this collection and that would work? And yeah, I could, but it's entirely possible that the span of these vectors, maybe it's not three-dimensional, as in maybe I don't need all 3 of these vectors in order to span that same row space. Maybe I can write the row space, the space created by all 3 of these things, maybe I can create that using fewer numbers of vectors. And this is what we're really looking to do. Okay? The computational aspects of this section are, can you create a basis that's a smallest possible spanning set, or a linearly independent spanning set? can I create a basis for my row space and my column space? We can, and not only can we, it's actually really, really easy. Okay, so let me go ahead and actually work out what the row space and column space for this matrix is, or at least get a basis for them, and then we'll talk a little bit more about what they are. Okay, so the first thing I'm going to do, I'm going to leave these definitions up here. Okay, the first thing we're going to do is we're going to put this into row echelon form. Now again, this requires a few different elementary row operations, but since I've done this same matrix many, many, many times, I'm just going to write it down. Okay, so the row echelon form for this matrix is this. Okay, that is an elementary row, an echelon form. Okay, so again, annihilate, pivot, more annihilation. We got it. So, in order to get from this matrix to this one, well, what we use are elementary row operations. And it turns out that elementary row operations don't change the space spanned by the rows. And that's fantastic, because what that means is that the space spanned by these rows is identical to the space spanned by these rows. And you might notice there are fewer useful vectors in this matrix. In fact, there are only two, right? The row of all zeros isn't useful. And in point of fact, the zero vector is never useful in any span. And so this row space is the span of my first row and my second row. Okay. Again, I don't need the zero vector. If you have extra zero rows, those are irrelevant. Okay. So this row space is the span of these, but that's the same as the row space of the original matrix. So this is the row space of A. Isn't that easy? Right? It's pretty easy, isn't it? Or what about my column space? Okay, so unfortunately, that's not a direct correlation. So I can't say that the column space of the row echelon form is the same as the column space of my original matrix. That's not true, because we did not use elementary column operations. We used elementary row operations. So that doesn't work. Okay? But they are correlated. Okay? So, in order to find my column space basis, what I'm going to do is I'm going to look in my row echelon form, and I'm going to identify the columns which contain my leading ones. So if we look in this particular matrix, we see that column 1 and column 2, they contain my leading ones, right? There's one of them, there's the other one. Okay, so column 1 and column 2. And it turns out that if I go back to my original matrix and take the same columns, column 1 and column 2, so the same columns as I got my lead ones from here, these column vectors form a basis for my column space. So I can say that the span of, look at these columns, 1, 4, 7, and 2, 5, 8 these form a basis for the column space of A. Okay? That's pretty easy, right? Yeah? We're in row echelon form. You can take the non-zero rows, they span the row space. Find out where your lead ones are. Take the corresponding columns from the original matrix. There's your basis for your column space. Okay? Now, I want to touch on a few things here. One, the concept of a basis, because I've used that word several times. Okay? A basis. This is a linearly independent spanning set. Okay? And you have to be a basis of something, right? So we're looking for a basis for the row space, right? A basis for the row space. Well, again, the row space is spanned by these three rows. Is the span of these three rows. That's clear, right? If I use these three rows, I take their span, I get a row space. The problem is these three rows taken together as vectors are not linearly independent. They're linearly dependent, right? Yeah? I know that because if I put them into row echelon form, the rank here is less than the number of vectors. Okay? So this, the span of this, is the same thing as the span of all three of these vectors together. The difference is these two are linearly independent. Okay? Now, why do we care about this? We don't necessarily from like a strictly being correct standpoint, right? I mean, technically, the span of these three vectors is the row space, but there's an advantage to using the minimum number of vectors possible. And that's really what the basis is, right? It's trying to write the span using a minimum number of vectors. The reason is these spaces are infinitely large, right? So technically speaking, I could write some sort of weird infinite list and say that the span of this list is the space, but that's somewhat ridiculous, right? I want to do things efficiently, and since that's the point, we're going to try and do them as efficiently as possible. Okay? So here's a basis for my row space and a basis for my column space. Now, I can go one step further, and I can start thinking about the geometry of these things, right? I know that these are linearly independent. The span of these things is my row space, but because of that, I can tell you how many dimensions my row space is, right? You see, when your set is linearly independent, then the number of elements in your spanning set is the same as the dimension, okay? So again, sort of writing that out, I can say, since the basis has two vectors, okay, 1, 2, then the dimension of the row space of A is 2. Okay? I say since the basis. Really this should be since a basis, but there's a theorem, we're not going to prove it, that every single basis for a space, for a vector space, has the same number of elements. So because this basis has 2 elements, every basis for this space will have 2 elements. Again, we won't prove that, but it is non-trivial. It's not it is something that needs to be proven. So what does this tell me? Well, if the dimension of this row space is 2, well then I can ask a couple relevant questions. 1, what the hell does it look like? And 2, where does it live? Well, let's answer that second question first. Look at the vectors that are in here. What type of vector is this? This is a vector with 3 components, right? This is a vector with 3 components. These vectors live in R3. Okay? They are 3 component vectors, and they have 3 real numbers as their component values. This is not all of R3, right? Because again, it's just a 1 2-dimensional space. But if I'm thinking about R3, the concept of a 3-dimensional real space, what is a 2-dimensional subspace? Well, it's a plane, right? Yeah, it's a plane. And so I can actually give you a little bit more information about this. I can say that my row space is a plane, that's a 2-dimensional space, in R3. Okay? I'm going to talk a little bit about the geometry there. Let's do the same thing for the column space, right? All these same things apply. Again, we're looking at the individual vectors here. I've got a vector, it's got 1, 2, 3 components, right? So these vectors also live in R3. Count the number of vectors we have. I've got 1, 2, 2 vectors. So this column space, it lives in R3 and it is 1, 2-dimensional. Well, then the column space is also a plane in R3. Now, I want to emphasize this. They're different planes, right? There's lots of planes in R3. These are different planes, but again, they both happen to be planes, and they both happen to live in R3. Okay? The computations for this are very, very easy, right? And in point of fact, I'm not going to do another example for column space and row space here, mainly because once you do a few of these and put them into your row echelon form, it should be pretty easy. Okay? All right, now, let's talk about the null space. You know, I did skip over the null space here, right? Well, let me give you a definition for the null space, and then after I do that, we'll talk about how to find it. Oddly enough, we're still going to use row echelon form here. So I'm just going to leave this this computation up, just because it's a little bit easier. Okay. All right. So the row space, I'm just going to give you the definition and then explain it. So the row space of any matrix A is the collection of all vectors such that A times that vector is equal to the 0 vector. Okay. Put simply, if I multiply A on the right by a vector, right? It's got to be, in order to make the multiplication make sense, it would have to be a vector. If I multiply A on the right by a vector, well, I'm going to get any number of things, but for some of those things, I'm going to get 0. I mean, for example, if I multiply it by the 0 vector, I'm going to get 0. The collection of all those things that you would multiply this by to get 0, that's the null space. But this might look a little familiar, yeah? A times V equals 0. Didn't we have something in one of our theorems that was like A times X equals the 0 vector? Yeah? Like the invertible matrix theorem? Yeah, we did. And in point of fact, remember this notation just represents a system, right? This is quite literally asking, if you take matrix A as the coefficients of a system, and you assume temporarily that that system is homogeneous, so it has a solution column of all zeros, okay, then its solution space is the row space. Okay? Now, the best part about this is, suppose I tack on an extra solution column here. Because I'm using elementary row operations, adding columns of all zeros has no effect on the operations I choose. So I already know what the row space result of this is going to be. The elementary row operation is just going to be, again, the same matrix with just zeros tacked on. That's it, right? Adding a column of all zeros to the end of a matrix doesn't affect the row echelon form in any meaningful way. It just adds columns of zeros onto it. And if this represents a system, then of course we know how to pull solutions out of that system. We have to use some parameterization, right? If I have, again, we'll call this x1, this one x2, and this one x3. I'll need to parameterize. So let's say x3 equals t. Going to my second row, that reads x2 plus 2x3 equals 0. So 1x2 plus 2x3 equals 0. Plugging in x3 as t gives me x2 is equal to negative 2t. And now taking both of those values and looking at my first row reads x1 plus 2x2 plus 3x3 3 equals 0. Again, putting in t for x3 and negative 2t for x2, we get x1 equals t. Again, just substitute in for x3 t, and for x2 negative 2t, and solve, you get x1 as t. So what does this tell me? This tells me that my null space is contains all the vectors that look like, so I'll write it down this way, but we still want a basis. This is not what we're looking for. My null space is the collection of all vectors in the form of t comma negative 2t comma t, where t is a real number. Okay. Now this doesn't give me a basis, right? A basis is written in the form of a span, but we can very easily do that by just choosing a value for each of our parameters, just an example value, right? So again, I know this is one-dimensional because notice that I only get one choice, right? I only have one parameterized variable here. So since I only get the one choice, just pick a value for that variable that will give you a vector. If I know it's one-dimensional, I only need one vector to span it. So if I let t equal 1, that gives me the matrix, the vector rather, 1 comma negative 2 comma 1, right? Well, then I can rewrite the null space as the span of 1 comma negative 2 comma 1. That's it. Now, of course, it's beneficial to sort of look at the geometry a little bit. Again, there's one element in this basis. There's one, so that's one-dimensional. Okay, where does it live? Well, look at the vector itself. It's got 1, 2, 3 components. They're comprised of real numbers. It lives in R3. So what is the null space? The null space is a one-dimensional space which lives in R3. Yeah, but what are those? Those are lines, aren't they? One-dimensional spaces are lines. They're lines that pass through the origin, right? So again, from a geometric standpoint, I know what this space is. This space is a line which lives in R3. Okay? It's a line living in R3. This seems fine. Now, as a real quick check, okay, since I've been worried, there's a reason I worked all these things on the same example. There's something called the rank nullity theorem. Okay? This is in section 4.9, the rank nullity theorem. Now, for us, right now, this is going to seem like just a nice sort of check at the end of our problem to make sure we got, something that's reasonable. In reality, it has a bit more far-reaching implications than what we're going to use it for right here, but that's for a later date. But what does the rank nullity theorem state? The rank nullity theorem just says, very simply, that n is equal to the rank of A plus the nullity of A. Now we know what the rank is, right? If I'm looking at this matrix, I know that n is the number of columns, so that's 3. Remember, this solution column doesn't actually exist, right? So it's 1, 2, 3 columns. I know the rank is 2, right? I know the rank is 2, 1, 2. And so whatever the hell the nullity is, I know that has to be 1. 3 is equal to 2 plus 1, right? But the nullity is just the dimension of the null space, which we already knew, right? Yeah, when we solved this, we saw that it was one-dimensional because I only got one basis vector. Okay? So the nullity is 1. And that's all the rank nullity theorem says. The rank nullity theorem says that the number of columns for any given matrix is always equal to its rank plus the dimension of its null space. That's it. So for us, this is a reasonably good check, right? Yeah? Because if I am working with a matrix who has 4 columns and I come out with a row space, with a rank rather of 3, and then a null space as dimension 2, I know I messed up, right? Because 3 plus 2 equals 5, and I don't have 5 columns to start with. Does that make sense? Okay. I want to work one more quick example for null spaces, if only because sometimes we'll get into a scenario where it won't be necessarily one-dimensional, and I want to sort of be very, very clear on how we come up with a basis here. So I'm going to take a very simple matrix, and I'm going to cheat a little bit. I'm already going to put it in row echelon form. So here I have a matrix. It's already in row echelon form, and I would like to know the row space of this, right? So not the row space, the null space. Well, again, remember the null space we're going to obtain by assuming it was a homogeneous system. So assume I've got that solution column of all zeros, and after that we solve this the way we'd normally solve a system. We need to parameterize. So I've got, again, x1, x2, x3, x4. Here are my lead ones, here and here, so I need to parameterize 2 of my variables. I'll let x3 equal s and x4 equal t. Second row here reads x2 plus 2x3 plus 3x4 equals 0. Substituting in s and t for x3 and x4 gives me x2 is equal to negative 2s minus 3t. Okay. My first equation, going up to my top row, reads x1 plus 2x2 plus 3x3 plus 4x4 equals 0. Again, I have substitutions for x2, x3, and x4. Let me write that out because I'm having trouble tracking it in my head. So x2 is negative 2s minus 3t. I've got plus 3 times s plus 4 times t, that equals 0. And so x1 in the end is, what's that? It's negative 4s and positive 3s, so that'll be positive s. That's negative 6t and positive 4t, that'll be positive 2t. Okay, so again, what do things in my null space look like? Well, they look like all vectors of the form x1, that's s plus 2t, s2, that's negative 2s minus 3t, comma x3, that's s, comma x4, that's t, where s and t are both real numbers. Now you'll notice that this one, unlike the previous example I gave you guys, doesn't have one parameter, it's got 2, right? And that implies that it's 2-dimensional. I get 2 choices when I create something like this. I get to pick S and I get to pick T. Those are my 2 choices. This is going to be 2-dimensional. I know it's going to be 2-dimensional. But that also means that in order to create a basis, I need 2 vectors, right? Not 1 like the previous example, I need 2. And because of the definition of how a basis works, those 2 vectors need to be linearly independent. So I don't want to go randomly picking values for S and T and plugging those in, and then just sort of getting vectors and hoping that they come out linearly independent, right? That's guessing, and sure it will work, but it's a little bit messier than we really want for a math class, right? In reality, there's a way in which I can choose values for my parameters to make sure that the vectors I'm pulling out are in fact linearly independent. Okay? And so what I'm going to do is I'm going to set one of my parameters equal to 1 and the rest of them equal to 0. So for example, to make my first basis vector, I'm going to set s equal to 1 and then every other parameter equal to 0. Now I keep phrasing it that way for a reason. If you have 6 parameters, you'll set the first one equal to 1 and all of the other 5 equal to 0, right? So the first one equal to 1, the rest of them equal to 0. And what I get whenever I plug that in is I get the vector 1, comma, -2, comma, 1, comma, 0. Again, literally plug these values in. Now to make every subsequent vector in my basis, what I'm going to do is I'm just going to change which parameter gets to be 1, right? So for my next one, I'm going to make t be 1 and everything else be 0, right? If I had more parameters, I would make the next one 1 and all the rest of them 0, right, in order to keep going. You'll notice that this is going to give me a different vector when I plug it in. It's going to give me specifically 2, comma, -3, comma, 0, comma, 1. Okay? Now the vectors I create in this way are guaranteed to be linearly independent. This is very useful. Because of that, I can use them as basis vectors for my null space. Okay? So my null space of A here, that's the span of 1, -2, 1, 0, and 2, -3, 0, 1. There we go. Okay? So there's my span, there's my basis for my null space. There are 2 of them, 1, 2, so it's 2-dimensional. We knew that already. Where do they live? Well, look at the individual vector. There's 1, 2, 3, 4 components, so they live in R4. So what is this? Again, geometrically speaking, it's a plane, since it's 2-dimensional, and it lives in R4. It's a 2-dimensional subspace. Okay? All right, guys. So these are not really that bad. It would be beneficial if when you did your practice, you made sure that you were doing the row space, the column space, and the null space for all of the homework problems that you do from sections 4.8 and 4.9. But again, these are purely computational. We will use these things later, okay? But for right now, this is what we need to know, okay? All right, I'll see you guys next time.